Hello, everyone. Welcome to our third talk as the Young Achiever Symposium sponsored by the Center for Socially Responsible AI at Penn State. So today we are delighted to have Kai Wang, who is a PhD candidate studying computer science at Harvard University, working with Professor Megan Timber. So prior to his PhD, Kai graduated from National Taiwan University with a bachelor in math and electronic engineering, where he won 2 silver medals at the International Mathematical Olympiad. Kai's work focused on providing actionable decisions to solve wildlife conservation and healthcare challenges. Both domains are multi-agent systems that requires using machine learning to address the uncertainty involved in the system and optimization to suggest actionable solutions. Kai identified the issues of solving machine learning and optimization problems separately, where he proposes various new techniques to integrate optimization problem into the machine learning pipeline to achieve decision-focused learning. So without further ado, please join me to welcome Kai for his talk.
Thank you, Hanji, for the great introduction. And I'm really pleased to be here to introduce my research on decision-focused learning. And the main idea, as Hanji mentioned, is to integrate optimization problem into training pipeline, and in particular to resolve social challenges. And I'm currently a 5th year computer science PhD at Harvard University. Yep. So my research, let me go through. My research has been focusing on the role of artificial intelligence in social change and how we can use artificial intelligence to solve social change. In particular, I focus on 2 domains, wildlife conservation and also healthcare. We have seen in the past that technology or artificial intelligence have been used to predict the poaching activity and therefore drive the intervention decisions to maximize the patrol performance in this wildlife conservation domain. On the other hand, healthcare, we also see technology and also artificial intelligence being used to create scalable solutions to improve maternal and child health, and also therefore improve the overall healthcare performance. And my research focuses on how artificial intelligence can actually help in those social changes. In particular, 3 different cases that I'm focusing on. The first one is the learning, and the second category is planning, and the last category is the deployment. One way to visualize or imagine these 3 components in artificial intelligence in the social challenge is to imagine in this data, to visualize in this data to deployment pipeline, where the goal of the learning component is to maximize or trying to model the social problems that we want to solve by creating a model or mapping to map from features to predictions to predict the uncertainty or unknown information in the social challenges. And the goal, of course, is to maximize the predictive accuracy. We want to learn a model that's as accurate as possible so that later we can use the model to drive decisions. And the goal of the planning component is to take the model that we just learned from the data and try to apply any kind of planning solutions to maximize the final decision quality, to find a decision that maximizes the decision quality. And lastly, the deployment component is to translate algorithmic solutions to real impact, to social impact, so that we can actually deploy our solution to the social challenge, to resolve those social challenges. So all these 3 components need to work together so that we can go from data to deployment to actually implement artificial intelligence into social challenges. However, there are different objectives in these 3 different goals. In particular, in the first 2, in learning and planning, we can see that those 2 goals actually had 2 different objectives. For example, in the learning component, all we want to do is just to construct a model that's as accurate as possible. But in the planning component, all we want to do is to find decision. Regardless of what the model is, we just want a good decision quality. We don't really care about whether the model is completely accurate or not. So the goals and also the objective in these 2 components are actually not identical. That is, they are not the same. So that motivates the main topic that I wanted to cover in this talk, which is decision-focused learning. So we still want to learn the model. We want to learn the model to predict all the uncertainty or all the unknown information in the social challenges, so that later we can solve that. But instead of maximizing the model to maximize the predictive accuracy, we may want to learn the model to maximize the downstream decision quality. And later, I will introduce how we achieve this. And the main idea is to integrate this planning component into a learning pipeline so that the learning process will be aware of the downstream decision quality. And throughout my research, I have been focusing on different parts of the learning and also planning and deployment aspect, in particular on the two main categories, the healthcare and also environmental policy. And my research also focused on trying to figure out how artificial intelligence can help in these three or four different components. And today, for today's talk, I'm gonna focus on decision-focused learning and also how we can also deploy user idea from decision-focused learning to achieve different ways of planning algorithms. And with a focus on this particular deployment, work with Google and also Ahmed on the healthcare domain. So let me first go through the first section about going from learning to decision focusing, how we can integrate planning problem to achieve decision focused learning. So this is a standard pipeline that we go from features to predict the models or social challenges that we want to solve, and later we can use a model to find the actionable decision in order to deploy. And in particular, the standard way, as I mentioned before, is to learn the model to just maximize the predictive accuracy. In particular, for example, some example we can do is to learn a neural network to predict the poaching hotspot in the national parks. Or we can also learn a neural network to predict where is the most popular computer that has cyber attack. And similarly, wildlife trafficking, we can also use loop features to fit into a neural network and make prediction on whether there will be trafficking activity happening in these loops or not. Let's use wildlife trafficking as an example. So, for example, we might have a network that we don't know the underlying trafficking activity, where there's any trafficking happening in this network or not. So what we can do instead is to take the features of each individual route and then fit into the model that we just learned, and then create prediction on the frequency of trafficking activities. And given these predictions, we will be able to construct a model, and therefore solving this game theory model or optimization models, we can figure out where to deploy our decision or where to intervene this smuggling activity in order to maximize the intervention performance or to stop the smuggling of illegal trafficking activity in this network. And once we deploy the decision, we will also receive a decision quality. And as we mentioned before, decision quality and also predictive accuracy are two different metrics. They are correlated, but they are not identical. So for example, if we accidentally made some mistake on the prediction. So for example, if the hotspots of trafficking activity is actually happening in the end of this network. So we may deploy the intervention resources on the wrong locations and therefore lead to a poor performance. Although we had a very high predictive accuracy because we made accurate prediction on almost every route, but we just missed the important routes, and that would significantly change our decision, our intervention decision, and therefore degrade the decision quality. So this is an example why predictive accuracy and also decision quality are two different metrics, and therefore why we want to, that motivates why we want to directly use decision focusing to maximize the decision quality instead. So the main idea to use decision focusing to directly maximize the decision quality is similar to what we had seen in the previous slide. We can still use the gradient descent or gradient ascent to backpropagate from the decision quality through the planning problem to the neural network model that we want to learn. We just need to run many iterations of gradient steps, and therefore we can learn the neural network that can make prediction and later being used to generate decision data. But the main challenge here is that there's a non-differentiable components in this pipeline, which is the planning problem. Unlike neural networks, planning problem it's more like an operational process. It's not explicitly differentiable. But fortunately, in the past, people have developed some technique by looking at the optimality conditions to figure out an alternative way to differentiate through the planning component. And therefore, this is how decision-focused learning is achieved. However, there's also a scalability issues, because in order to run decision-focused learning for every single gradient step, we have to solve the planning problem in order to get a decision, get a new decision. And also, once we get the optimal decision, we also need to backpropagate to the planning problem again. So for every single gradient step, we need to solve the problem and also backpropagate through the problem. And we need to run hundreds, thousands of iterations in order to just train one single neural network. This is definitely not scalable, especially when the planning problem becomes more and more complicated. And just to elaborate more, in the forward path, in this context, we consider solving just a planning problem as a non-convex continuous optimization problem. What we want to do is to maximize the objective here, parameterized by our decision variable x and also the prediction theta, subject to some linear constraint. So in the forward path, all we need to do is to solve the planning problem. Given the prediction from our neural network, we need to solve the planning problem to figure out what's the current optimal decisions. And in the backward path, we need to backpropagate from the decision, optimal decision at start, to the predictions and then therefore to the neural network. And this process has to repeat every single gradient step. So that motivates our first contribution, first paper published last year in Neuralist. So I think there's one.
Okay, you mean the problem is convex in X, but non-convex in theta, right?
It's non-convex in X and theta.
Okay, and then this Amos paper can solve this problem?
No, that one
right.
can
okay.
only solve the Cochati program, but the same idea can also be generalized. So there's one follow-up where that generalized from Cochati optimization to convex optimization. And we also generalize from convex optimization problem to non-convex optimization problem, as long as that's smooth. The main idea generalizing from convex to non-convex problem is to locally approximate the non-convex problem by a convex problem. So you can think of like around at the optimal solution, supposing that you are minimizing or maximizing the objective, then locally that objective is either convex or concave. So to some extent, you can reduce that to the standard convex optimization and therefore backpropagate from there.
Thanks.
Yeah. Cool. Thank you for the questions. Yeah. Okay, so we have seen that like in the forward pass and also backward pass, both processes are expensive. We need to repeatedly solve the problem, and also we need to repeatedly differentiate through the problem. Both these operations depends on the complexity of the planning problem. As long as our planning problem in the social challenges becomes more complicated, especially in real world size, then these two processes can both become very expensive. So the main idea in this work published in Neuralist 2020 is to use a surrogate problem instead. So since the original planning problem is expensive to solve and also expensive to backpropagate, so maybe we don't want to backpropagate and also solve the original planning problem. What we want to do is to construct a surrogate problem. So instead of solving the original problem, we go through the surrogate problem. We just solve the surrogate problem, and then reconstruct back to the reconstruct the decision from the surrogate problem instead of from solving the original planning problem. And additionally, this surrogate problem is not just a random surrogate problem. The way that we construct this surrogate problem is to reparameterize the original planning problem, reparameterize the high dimensional decision variable x by projecting x to y, to a lower dimension of y. So in this case, the surrogate problem will be parameterized in terms of y, and y is much lower dimensional than the original x, higher dimensional x, and therefore solving the surrogate problem will become much cheaper and also much cheaper to backpropagate through as well. So all we need to do here, one way to visualize this is to use a network smuggling problem as we introduced before. So original network problem, we had a lot of decision variables that we need to consider. We need to consider whether we want to put intervention on this route or not, and also so there's all the edges in the network. So this surrogate problem, to some extent, is like we can group these decision variables together. So for example, we just group all the blue edges to form a giant meta variables. And then we just have one single variable controlling each individual colors, each individual groups. And then that will construct our surrogate problem. And as you can see, we largely reduce the dimensionality in this problem. And as I mentioned, because the surrogate problem is much cheaper, so we can easily solve the surrogate problem, and also so does the backward pass. We can backpropagate to the surrogate problem. And also this becomes much cheaper because the surrogate problem is much smaller, lower dimensional. But the bad news is that this can actually destroy the decision quality, because it's very likely we are not using a reasonable surrogate. The surrogate problem might not even represent the original problem. We may use a random surrogate to reparameterize the original problem that doesn't even capture the optimal solution at all. So the solution to this issue is to keep the surrogate parameter, in this case, the surrogate problem, flexible. So what we're gonna do here is to add an additional backward pass to update the surrogate parameter P here, so that we can also backpropagate gradient from the final decision quality to the planning problem and also to the surrogate parameter, so that we can tune the surrogate problem to maximize the final decision quality. In this case, surrogate problem will be tuned to align with the original planning problem in order to capture the optimal solutions. And therefore, we will no longer just use a single fixed surrogate parameter. We will gradually change the surrogate parameter and therefore the surrogate problem to align with the decision quality. Turns out this works very well. We can improve the decision quality while simultaneously maintain the scalability in the forward pass and also the backward pass. And the main takeaway here is that we achieve dimension reduction by using this surrogate approach. And dimension reduction can apparently improve the scalability in both the forward pass and also the backward pass. And additionally, we also want to jointly learn the surrogate with the model. We don't want to use a fixed surrogate because fixed surrogate can create catastrophic consequence. So we want to maintain a flexible surrogate and therefore gradually update the surrogate as well. So that's the first way to resolve the scalability issues. I'm gonna present the second way to resolve the scalability issue in this pipeline as well. This is called Brock decision focus learning and published in August 2020. And the main idea here is actually very similar to the work that I just introduced. So the main idea here is to just backpropagate through, because backpropagate through the entire planning problem is expensive. So what we can do here is just to backpropagate through a subset of decision variables. We don't want to backpropagate through all of that. We just want to backpropagate part of it. And again, using the previous example to explain. So in order to backpropagate through the planning problem, we need to backpropagate through all the decision variables in this network, all the edges. Instead, what we can do here is to sample or randomly select some edges as a new decision variables that we want to backpropagate, and then we just reformulate the original planning problem to this partial set of planning problem, and then we just backpropagate from there. So what we can do here is, in the forward pass, we still solve the original planning problem, but in the backward pass, we just reparameterize or reformulate the planning problem to allow just a subset of decision variables as our decision variables, and we can keep everything else fixed and just backpropagate from this subset. And apparently this can resolve the computation cost in the backward pass. But the question here becomes, is this even valid, or is this even reasonable to do like a subsampling or subset of decision variables? And the answer is that we can actually build some approximation guarantee in the backward pass. In order to compare the gradient that we compute from this new method, we can compare the gradient with the original decision focus learning. So we can use trend rule to decompose the gradient that we will be using to backpropagate from the decision quality to the prediction, and then finally to the model parameters. And then it turns out that the first term, we obtained from these two different methods, they are actually identical, except in our method, because we are only backpropagating through a subset of decision variables. So we actually lose linearly amount of information because we only backpropagate through some of them. But it turns out that the second term that we want in order to compute the derivative of an optimal decision or to the prediction of the optimization problems, this term we can actually prove that they are actually close to each other. But on the other hand, we only need projected less computation cost because the effect of dimension reduction, we only need to backpropagate through partial set of our decision variables, and therefore the computation cost can be reduced projectically. And therefore, overall, we get a linear speedup because we lose linear amount of information, but the computation cost is projected less. So the main takeaway in this part is that we can also achieve dimension reduction using another way, like by sampling subset of decision variables to backpropagate. And in this way, we can actually achieve approximation guarantee. In the previous surrogate method, there's no approximation guarantee. But in this version, we can achieve approximation guarantee instead. So just a summary of these two different methods. So we implement decision-focused learning, different variants of decision-focused learning, and also two-stage method, which is just to maximize the predictive accuracy on the smuggling intervention problem. And we are plotting in tensor degree, and therefore the lower, the better. When we see that two-stage method, there's no scalability issue because we don't need to solve the optimization problem in the learning process. So there's no scalability issue. But on the other hand, the performance is also poor because we are just maximizing the predictive accuracy. We are not maximizing the decision quality. But on the other hand, decision-focused learning, as we introduced before, there's a poor scalability because we need to repeatedly solve the forward pass, solve the planning problem, and also backpropagate through that. But it can achieve, apparently it can achieve better performance than two-stage method. And second, our Brock method can achieve better scalability as we had shown. It can reduce the decision variables that we want to backpropagate through and therefore achieve better scalability in the backward pass. On the other hand, it can also achieve good performance because we can also build an approximation guarantee. The gradient we compute from the Brock version is actually close to the gradient we compute in the decision-focused learning version. And lastly, the surrogate method can achieve the best scalability because we can reduce the computation cost in both the forward pass and also the backward pass. And simultaneously, it can gradually improve the surrogate to improve the performance as well, but there's no guarantee. Yeah.
So when you use the P matrix basically to project, wouldn't the projection method do same as block method if the block method is the best, because ultimately it will choose those decisions on which you can do better, and right?
Yeah, that's a good point. So one way to link these two methods together is so the Brock method will be, to some extent, it's just like having a binary P matrix. You only map we had a binary mapping between decision variables to the new subset of decision variables. In the previous surrogate approach, that P matrix is a continuous matrix. We don't maintain just a binary matrix. So in fact, you can just have a fraction of values controlling each individual variables instead of just 0 and 1s. But on the flip side, we lose optimization. So we lose approximation guarantee there. We don't know whether there's any, because we can keep arbitrary projection, and therefore we don't know whether there's any approximation guarantee. Yeah. So beyond this smuggling intervention problem, we also deployed we also implement the algorithm to the movie recommendation problem and also portfolio optimization problem. We also see a similar trend between two-stage decision-focused learning and also the surrogate method. We do not implement the Brock version on these two domains though, but we see that surrogate method can actually improve both the scalability and also the performance, surprisingly also the performance as well. So this is to our knowledge, this is the first study on scalability issue of decision focus learning. And in this case, we provide two alternative ways to resolve the scalability issues in decision focus learning. Yep. So I'm gonna proceed to the next topic. So far we only cover one-shot decision. So basically all the problem that we are considering is just an optimization problem. Given the predictions, we want to come up with the optimal decisions, and therefore that's the end of the pipeline. So what the next topics that I cover is how decision focus learning is generalized to sequential decision making. So we still have the same pipeline here. We still want to learn the model that map from features to predictions, but in contrast to the previous pipeline, here we might have the sequential planning problems that we will be solving, and therefore the subsequent solution will become a sequential policy, and therefore the solution quality will also become a sequential policy quality instead. And some examples of this pipeline is patrol planning problems with unknown snare probability of placement. So imagining that we are in a new national parks, we want to patrol these new national parks, and there could be snares like being placed in different locations, but we do not know the probabilities, and also we don't get to observe those snares. What we can do is to first learn the mapping to predict from location features like terrain features or animal density feature in each locations, to predict what's the probability of observing a snare there in that locations. And then in particular, snare can respawn, and therefore this becomes a sequential planning problem. We had to determine where we want to patrol based on whether we observe a snare in that location or not. And similarly, in the healthcare domain, there's also a sequential planning problem involved in the healthcare domain. So in this domain, we consider a group of models that they are engaged in a healthcare program. And the healthcare program will just provide automated messages to provide health information to this model. And all we want to do is we want all these models to engage with the program. But apparently models can stop engaging with the program because those are just automated messages. So what we can do instead is to just schedule some service code. Whenever we observe models stop engaging with the program, we just schedule service code, try to retain the engagement of models so that hopefully we can convince them to engage with the program. And you can see that this is also a sequential planning problem. We had to first make prediction on each individual models. We can use the demographic features of each model to predict their behavior of engagement behavior. And then based on the predictions, we can determine how we want to schedule the service code, and also based on the observation of whether they stop listening or stop engaging with us. So apparently there are applications of sequential plannings involved in this pipeline. And the next question is, how do we solve that? So one natural way, or one common way to solve this problem is just as we described. We can try to learn a model to maximize the predictive accuracy. So for example, in the patrol planning domain, we can first learn a predictive model trying to predict the underlying poaching risk of each individual locations. And once we finish learning a model, we can start doing the patrol planning. We can start doing the sequential planning problem later. Or in the healthcare domain, we can also learn a predictive model to predict models' engagement behavior. And then later, once we have learned that model, we can decide how we want to solve the sequential problem later. But in contrast, as we mentioned before, predictive accuracy and also the solution quality are two different metrics. There are examples showing that they don't match to each other. So maybe we also want to use the idea of decision focusing to directly learn a model to maximize the final policy quality or solution quality whenever there's a sequential planning problem involved. And the main challenge in this case is that there's a sequential planning problem involved. Previously, we know how to differentiate through the planning problem by, for example, looking at the optimality conditions. We can differentiate through optimality conditions. But in this case, we had a sequential planning problem. It's a sequence of decision-making process. So we don't know how to, at least in the past, we don't know how to differentiate through the sequential planning problem. And the main contribution in this work is a method to differentiate through a sequential planning problem. And the main idea is all we want to do is to compute a derivative of the optimal policy with respect to our predictions. And the main idea is similar to what we had seen in the one-shot optimization problem. We can look at the automatic conditions in this context, in the sequential planning problem. In particular, we can look at the policy automaticity. This is common in the literature of reinforcement learning that the optimal policy must maximize the expected cumulative return. Otherwise, it would not be an optimal policy. And we can look at the necessary condition of this automatic condition, which is at the optimal solution, there should be no gradient. Otherwise, you can just run single gradient step to improve your expected cumulative return. So at least the gradient needs to be 0. And therefore, we can compute the total derivative of the gradient and therefore derive the following linear equations. And we can see that suddenly the gradient that we want to compute, the derivative of optimal policy with respect to the prediction suddenly pops out. And therefore, we can just solve this linear equation to compute the derivative of the optimal policy with respect to the predictions. And in this context, unlike the standard optimization problem, the objective here, the expected cumulative return, is implicitly defined. We don't have a closed form expression of the expected cumulative return, and therefore the standard auto differentiation tools does not apply here. So all we need to do here is to apply policy gradient theory to compute the derivative of this expected cumulative return. It's just similar to the policy gradient algorithm or policy gradient-based algorithm that commonly used in reinforcement learning domain. And by using policy gradient theory, we will be able to compute an unbiased estimate of these two terms and therefore solve the linear equation accordingly. And the main consequence or main takeaway here is that we will be able to differentiate through the sequential planning problem. So as we have seen in the past, as long as we can differentiate through the planning problem, either one-shot optimization problem or sequential planning problem, we will be able to achieve decision focusing to directly maximize the final policy quality or decision quality. And therefore, we provide the first decision focusing in sequential problems by looking at the automatic condition in the sequential settings. So lastly, I'm gonna show you one application in maternal and child health. In particular, this is an application of decision focusing in sequential decision making. So this maternal and child health application is a program run by a non-government organization called Wang in India. And their goal is to use automated messages to provide health information to mothers in India, for example, like what I mentioned before. By providing this health information to mothers, we can actually avoid a lot of preventive diseases by, for example, some disease could be caused by micronutrient deficiency. And therefore, as long as mothers being aware of this information, they could prevent from those diseases from being happening, and therefore improve the maternal and child health. And the challenges, unfortunately, in this case, is that mothers may stop listening to the automated messages because the automated messages are just automated messages. People commonly can just stop listening to the automated messages. And the solution they adopt in this program is to just schedule some actual human or actual healthcare workers to make service calls and also talk to the mothers and also convince they to continue engaging with the program. And therefore, we can achieve the best performance, get best engagement performance, and hopefully improve the maternal and child health. And you can see that it's a sequential planning problem because we need to make decisions depending on how mothers engage with the program or not. And I also wanted to highlight this. This program is not the program is actually a very large scale. There were at least 200,000 people, 200,000 mothers and children involved in the program in just one single year between 2019 to 2020. So we had to resolve all the scalability issue, otherwise decision focusing would not be able to apply. So just some brief overview of what the model that we want to learn. the model that we want to learn here is we can use demographic features to predict models' transition probability, whether they transition from engaging state to non-engaging state, so that later we can use these predictions to determine whether we want to call these models or not. And later we will solve the sequential problem, as I mentioned. And in the past, people have been using just a standard two-stage learning approach to maximize the predictive accuracy. We can learn a single model that maximizes the predictive accuracy on the transition probability. And this actually turns out to be very well. And in a recent study by Mate et al. Published at AAAI this year, they achieved a 32% of reduction in terms of engagement drops. So they can prevent 32% of models from dropping the engagement with the program. And similarly, we also observe the same trend in our simulation. We can see that two-stage approach by learning a model to predict the transition probability, we can improve the performance, engagement performance, than just randomly scheduling service code to code these models. And of course, the questions to ask here is, can decision focus learning further improve this performance? Because we have seen decision focus learning is able to, by focusing on the right objective, you are able to improve the performance. And we have seen is that the initial study is that we see that decision focusing actually can improve a lot against the two-stage approach. We can actually achieve similar amount of improvement going from random to two-stage and from two-stage to this decision focus learning. But unfortunately, the cause will be, as we mentioned before, there are a lot of scalability issue in both the forward pass and the backward pass. In particular, in this case, the forward pass, we need to solve the sequential planning problem. Unlike before, we had the optimization problem, sequential planning problem can be even more expensive to solve. And so there's a backward pass, as we mentioned in a previous study. In order to backpropagate through a sequential planning problem, we had to apply policy gradient theory and all the stuff that we introduced before. Those are all very expensive to backpropagate through. So the main contribution in this work is how we resolve this scalability issue in a sequential setting, and therefore deploy and apply this algorithm to the real world domain. So similar to what we have seen in the surrogate approach, we may want to use an alternative way to solve the planning problem. We probably don't want to solve the original problem. So what we can do here is to leverage the problem domain specialty in this case. In general, in this case, we don't have a general sequential problem we want to solve. In this case, we actually had just a restless multi-unbanded problem. It's a generalization of multi-unbanded problems that every single time step we need to determine one single a set of arms to pull. So it turns out that restless multi-unbanded, there's an approximate solution that we can solve the restless multi-unbanded problem approximately. In particular, it's called Whistle index. So instead of using the original problem, solving the original problem optimally, solving the restless multi-unbanded problem optimally, we can actually use this domain-specific solution, approximate solution, to solve the problem approximately using Whistle index policy. So all we need to do is to take the predictions on the transition probability to compute the Whistle index, and then based on the Whistle index to determine which set of models or which set of arms to call. This will be the policy that we will be using for solving this restless multi-unbanded. So this policy is an approximate solution. It's not optimal, so we had to figure out different ways to backpropagate through. We cannot use the previous KKT or optimality conditions, the idea of optimality condition to backpropagate through. So all we need to do is to backpropagate through this top K selection and also the Whistle index computation in order to backpropagate through gradient. But the good thing is that we will be able to improve the scalability because we no longer need to go through the solving the restless multi-unbanded and also backpropagate through that. We just need to go through this approximate solution instead. And it turns out it also improved the scalability a lot. And we are able to apply this to real world problem. And the takeaway in this section is that maybe we don't want to always use KKT condition or optimality conditions to backpropagate gradient and also solve the problem. Maybe we want to use or leverage some domain-specific solution to bypass the cost of differentiating and also solving the sequential problems. And it really depends on the problem that you are solving. And as we have seen before, we can see the same amount of improvement going from random to two-stage and from two-stage to decision focused learning. And I also wanted to highlight the predictive accuracy of these three methods. So in fact, two-stage method can achieve the best predictive accuracy because two-stage is trained to maximize the predictive accuracy. But you can see that on the right-hand side, that predictive accuracy does not translate to the best performance in the engagement performance. Actually, this decision-focused learning can sacrifice or can lose some predictive accuracy, but on the other hand, achieve higher or better engagement performance. And to our knowledge, this is the first decision-focused learning on real sequential problem because the previous study that we had in the neurus doesn't scale up to large-scale problem. Apparently, we had to differentiate through all the KKT conditions and also the policy gradient theory. Those are all not scalable. And our next step, we are actively working with this non-government organization, Amen, to deploy this decision-focused learning, and we are hoping to get a real evaluation on our method in decision-focused learning. And lastly, I also wanted to talk about how the idea in decision-focused learning can be used in the planning component, in particular, in this case, the multi-agent planning. So in this case, we consider stackable gains with multiple follows. And I will later show you there's a very similar, there's an analogy between stackable gains and also our pipeline of decision-focused learning. So in this context, stackable gains with multiple follows, we had a leader who has to commit to a strategy first. Once the strategy is chosen, all the followers get to see the strategy, and then they will move and also determine their own strategy simultaneously to finally form an equilibrium. And that's the leader will receive a payoff and also a constraint cost, depending on the follower's equilibrium and also the leader strategy. So it turns out this has many applications in wildlife conservation, cybersecurity, and also public health, etc., because there could be multiple followers involved in all these domains. And as I mentioned, there's an analogy of stackable gains and also the pipeline of decision-focused learning. So instead of having a machine learning models that make prediction and then later prediction is used to solve the optimization problem, in this case, we had a leader who can directly control the prediction or control the policy. And then the policy is later fed into a multi-agent planning problem, and therefore all the followers will jointly decide a decision, or in other words, Nash equilibrium. And then that's the quality or solution quality is evaluated on the Nash equilibrium instead. So the idea in decision-focused learning can also be applied here because we know how to backpropagate from the decision to the prediction, in this case, the policy. So we actually can apply the same idea to achieve a gradient descent or gradient-based algorithm to solve stackable gains with multiple followers. In particular, the main contribution here is how to differentiate through the multi-agent planning and how we differentiate through the Nash equilibrium. And we differentiate through that by concatenating all the KKT conditions of all the followers together to form a giant KKT condition. And we can just apply the same technique of differentiating through KKT condition to differentiate through this giant KKT condition. And therefore, we will be able to backpropagate gradient from the equilibrium to the policy. And therefore, we achieve this differentiability of Nash equilibrium. And also, we also achieve differentiability in multiple equilibria in the paper as well. And as if this will achieve a gradient-based, this will eventually lead to a gradient-based algorithm to solve stackable gains with multiple followers, which previously people usually solve this kind of problem by optimization or by level optimization approaches instead. And lastly, I also wanted to highlight the importance of deployment and collaboration. So I am currently actively working with Amen to improve this on this maternal and child health domains. And also I'm also working with citizens of the Earth, Taiwan, in order to provide environmental policy. What I'm saying is that the lesson we learned from decision-focused learning is that it's important to incorporate decision-making process or planning problem into a learning pipeline so that we can align the objective in the learning and also in the planning components. But we can also see that there's also an additional deployment process in this data to deployment pipeline. So it's also very important to incorporate the deployment process to gradually adjust our planning problems, and also therefore our learning component in order to achieve a data to deployment pipeline and to maximize the deployment performance. So that's a lesson that I learned from the decision-focused learning, and also I'm working with this non-government organization to deploy our algorithms to achieve social impacts. So in conclusions, I just wanted to highlight decision focusing. The goal that we achieve in decision focusing is that we can address the important issues of mismatch objectives. In the learning components, we are trying to maximize the predictive accuracy, but in the planning components, we are trying to maximize the decision quality. And decision focusing is a way to address this mismatch objective, the issue of mismatch objectives. And another way to think of decision focusing is that it can actually incorporate prior knowledge of planning problems into the learning pipeline. Because we get feedback from the planning problems, we know whether these predictions lead to good performance or not. We can actually get feedback from the planning components and actually incorporate this prior knowledge to make the prediction or make the predictive model perform better. So to some extent, this is similar to incorporating prior knowledge, just like people use regularization term in computer vision or in natural language processing. They all want to incorporate prior knowledge of the test you are solving. In this case, decision focusing is also using, by integrating these planning problems, we can also incorporate prior knowledge to the learning pipeline. And technically, the main technique we bring in this decision focusing is the different kind of differentiability in different various planning problems. And we have seen scalability is one major issue in all these algorithms, in all these problems. In particular, I wanted to highlight that the adaptation to different planning problems is important. We have seen in the previous Armin study, the real deployment case, that maybe we don't need to go through the KD condition. KD condition might be an overkill. It's too expensive to compute and too expensive to backpropagate. So maybe there's a different ways to backpropagate through the planning process, and it really depends on the planning problem that we are solving. So it's important to adapt to different kind of planning problems. And with that, I would like to conclude my talk. And yeah, please feel free to send me a message, and I'm happy to take any questions.
Thank you, Kai, for your wonderful talk. So do we have questions from the audience?
I can start if there is no question. Yeah, so thanks for the very clear presentation. I mean, it was very useful for me. Yeah, so I have a question, like, so there is a planning part, and for that you have a parameter theta. You learn the parameter theta. In some way, we can say that this is a decision-focused learning or end-to-end learning. Then there is a part of deployment, right? You deploy this model. Now, any kind of model that is deployed leads to some kind of, it's an intervention policy. And an intervention policy might change the behavior of the population. Suppose I am interdicting certain illegal flow of drugs. Now, the moment I deploy some police force, what will happen is that the traffickers would change the route. So do you think that there is some way in which this causal part could be incorporated into the decision-focused learning part in the future? Or is there some work where this has been done?
Yeah, that's a good question. So I think what you are referring to is similar to basically what we consider throughout this talk is an offline problem. Basically, once you make the decision, once the problem, the parameters is predicted, then the problem is given and there's nothing changed afterward. And what you're saying is like, maybe your decision or your actions in the sequential planning problem can also impact the problem that we are solving. So to some extent, that's like the idea of online learning. So far, we were trying to apply decision-focused learning to online learning. So basically, a later planning part component is more like an online planning process, either multi-ambiguity problems or some other reinforcement learning problem that has online feedback. But now, so far, I'm not aware of any like works that achieve like decision-focused learning with online learning. But that's definitely a feasible direction. And actually, that's very important in real world, especially in this social change. The decision you make can also can affect the problem that you are solving. There's a feedback loop that can affect the overall problem. So, for example, in the maternal and child health, the way that we deploy like the scheduled service code can also impact their engagement behavior. They might change their behavior and therefore change our prediction as well. So far, everything is offline, and therefore once the prediction is met, there's nothing changed. But what you say is definitely a feasible action. And also that's aligned with what real world is happening. So
thanks.
Okay, do we have other questions? Yeah, so I have a question about the maternal health application. So I saw your diagram that, you know, for two-stage, the accuracy is pretty high, right? Compared with the decision focused learning. But it does not translate into a better decision quality. So my understanding is that maybe because, you know, the model's prediction, they are making mistakes on some significant part that can impact the decision. So planning, is that the case, or, you know?
Yeah, that's a good observation. So yes, predictive accuracy doesn't. One of the reasons that predictive accuracy doesn't translate to decision quality is because you make like mistake on important targets. So one way to fix that using like two-stage learning is to maybe you put higher weights on the more important targets or predictions. For example, in a patrol planning problem, we want to predict whether there's a poaching activity or not. And as you can imagine, most of the majority of, or let's say a national park, there's no poaching activity happening at all. Only a few spots has poaching activities. So apparently a predictive model that always predict like zeros or negative will achieve very high predictive accuracy, but that's not useful at all. So one way to resolve this issue is maybe you can consider weighted predictive accuracy, that you put higher weights on the more important targets, on the more important prediction, and then that can more or less resolve the mismatch between predictive accuracy and also the decision quality. But it really depends on the problem that you are solving. It depends on like how you know that, whether you know how to put weights on different targets, on different predictions. And I would say decision-focused learning is not limited to that. You can actually just incorporate a planning problem into a learning pipeline without knowing the underlying weights. You can just incorporate a prior knowledge from the planning problem instead of prior knowledge of how you put weights on targets. But that's a good observation, I would say.
Yeah. And also I was just thinking, you know, out of box, you know, because this two-stage, you know, optimization, it's like an end-to-end training or end-to-end optimization. So is that a way just, you know, let's say design, let's say deep reinforcement learning agent. So we just train an agent, let's say it's a black box neural network and output action. So is that, you know, applied to this problem, or is there some limitations to this kind of approach?
Yeah, so there's works in offline reinforcement learning. They are actually trying to do similar things where you are given a set of data, and you may want to use the data to construct maybe some historical observation of how you interact with the environment. And then based on the data, you want to construct, let's say, the reward function and also the transition probabilities. And so that you can later construct a policy later as a final policy you may want to use. But in the past, in the literature, like saying in offline literature offline reinforcement learning, people do not consider like the presence of features. People usually assume there's just a trajectories. You have historical interaction with the environment, and then you can use the historical interactions to reconstruct the model, reconstruct the rewards and the transition probability. This does not apply to our case, especially in this patient or in this mother's maternal and child health problem, because we don't actually get to see historical interaction between these models, because models usually only participate in the program once, and then once they finish the program, they will just be gone forever. You never get to see the same person twice. So it turns out that we don't get any historical interaction or historical data from the same environment. So all we need to do is to have an additional features that map from features to predictions and later to policy. So that's like that's a literature of offline IO. But what you say is also correct. Maybe we can also construct another like a giant reinforcement learning agent that can map all the way from features to policy. But yeah, I'm also not aware of any work on that. But I believe the performance might be bad because you had to deal with all the issues involved in this huge challenge. You need to make prediction and later solve another sequential problem. So I believe, yeah, this pipeline may be a simpler way to look at that problem though.
Okay. So do we have other questions from the audience?
I have a technical question. So I differentiated through the, like I use CVXPY, I suppose, to compute the gradients. It uses a differentiation of the KKT conditions. From what I observed is that the gradients are noisy. Have you, I mean, very noisy. Is it the case? Have you looked at them like in your research as well?
Yeah, that's correct. So depending on how smooth your problem is, as long as your problem is like smooth enough, like the Haitian, the eigenvalue of your Haitian is large enough, then you will have a much stable estimate of the gradient. But as long as the problem is not smooth, in that case, if the gradient, sorry, I think if a grid, yes, I do see the same issue, and the way that we resolve that issue is to add an additional constant identity matrix to the Haitian terms in order to backpropagate through the KKT condition. So we don't directly use CVXPy because it doesn't allow you to change how you backpropagate from KKT conditions. So we actually implement how we differentiate through the KKT conditions, and we added regularization term to the Haitian term, to the second order derivative, and therefore it will stabilize. It will make the second order term more stable, because if the second order term is close to 0, in other words, it has a very small eigenvalues, then the inverting that second order term can cause a giant noise or giant perturbations. So what we do here is to add a constant identity matrix to that Haitian, to the second order term. That would make the overall estimate of gradients more stable, although it would change the gradient, but at least we can get a more stable components.
Okay, thank you. Because I was looking at like a problem, I boiled it down to like a single parameter problem with a square objective. It's a mean square loss kind of an objective. And even the planning part of your optimization problem, it's also quadratic. So I knew, I know the closed form solution for that. And the gradients that we get from the KKT condition are like quite noisy. So I was wondering whether there is, I mean, it's common in this field about.
Yeah, very common. Yeah.
Okay.
And in the quadratic case, what you might want to do is to maybe add a quadratic term to your quadratic constant, quadratic matrix, so that the quadratic parameter will be less singular. As long as that quadratic term is less singular, then your solution will become much more stable, because similarly, solving quadratic optimization also depends on the singularity of your quadratic term, right? So adding a regression term will help a lot.
Thank you very much.
Yeah, thank you Thanks, everyone. So thank you, Kai, for this wonderful talk. And yeah, thanks everyone for attending this talk. And our next talk will be next week. So stay tuned as well. Yeah.
Thank you for having me here. Really great.